this video, we are going to talk about differentiability and continuity. Remember, for a function to be differentiable at a, then this limit, the limit as h goes to 0 of f of a plus h minus f of a over h exists. And don't forget our equivalent way to write this same limit, the limit as x goes to a, f of x minus f of a over x minus a. If this limit exists, then we say that f is differentiable at a. And remember back that if the limit as x approaches a of f of x equals f of a, then we say f is continuous at a. So the question that we are going to explore in this video is where these two agree. If they ever agree, do they always agree? All right? And it turns out we actually have a theorem. And that theorem is if f is differentiable at a, then f is continuous at a. Okay, so if it is differentiable at a, it is continuous at a. So what does that mean in terms of our limits? And I'm going to use the second form of the definition of the derivative. If the limit as x goes to a, f of x minus f of a over x minus a exists, so if that limit exists, then this limit exists. That's what this theorem says. If it's differentiable at a, it's continuous at a. So let's see if we can show that algebraically. We're going to start with this, and then we're going to show this. All right? So let's start with this fact. Do you agree that f of x minus f of a is equivalent to f of x minus f of a times 1? I'm sure you do. Let's write this like this. This whole thing times 1? Sure. Well, that means I can write f of x minus f of a as f of x minus f of a times x minus a over x minus a, provided that x is not a. Because as long as x is not a, this quotient is equivalent to 1. All right, so this is equal to f of x minus f of a over x minus a times x minus a. I've just split up my fraction, right? So f of x minus f of a is equal to this product over here. Okay? Now I'm going to move that over. So f of x is equal to f of x minus f of a all over x minus a times x minus a plus f of a. Okay? All right, we're ready to take the limit. So if I look at the limit as x approaches a of both sides of f of x, it's equal to the limit of the right-hand side, x approaches a, of f of x minus f of a all over x minus a times x minus a plus f of a. Right? I've just taken the limit as x approaches a of both sides. Now, I can split this limit up, this product, provided that each piece of this product, that limit exists. And we know this limit exists, and this is where we bring in our hypothesis. We know this limit exists because f is differentiable at a. So this limit, x approaches a, f of x minus f of a, x minus a, is actually equal to f prime of a. Right? Because the derivative exists at a. This becomes, well, as x approaches a, that becomes, I can do direct substitution, a minus a times 0. Plus, and we know the derivative, the limit of as x approaches a of a constant is just that constant. So, the limit as x approaches a of f of x equals, that goes to 0, f of a. And that's the definition of continuity. Therefore, f is continuous at a. So if we start with the premise that f is differentiable at A, we get that f is continuous at A. That's going to be useful. Now, here is what our theorem does not say. It does say this. Let's write what it does not say. It does not say if f is continuous at A, then f is differentiable at A. It doesn't say that at all. Remember, if a if-then statement is true doesn't mean that its converse is true. So if f is continuous at A, then f is differentiable at A is not necessarily true. And I'm going to give you a classic counterexample. Consider f of x equals the absolute value of x. What we saw in previous videos, well, first of all, let's sketch the graph. And so our graphic definition of continuity is I can sketch this graph without ever lifting my pen, right? I know that f is continuous for all x values. So in particular, it's continuous at x equals 0, right? There's no hole, there's no asymptote, there's no jump. However, what I also know is f is not differentiable at x equals 0. So this is a case where continuity does not give differentiability. So remember that. Let's summarize. Differentiability implies continuity, but continuity does not imply differentiability. That doesn't mean if you're continuous, you're not differentiable. It just means if you're continuous, you aren't necessarily differentiable.